Okay, so today we're going to do the week 9 presentation, class for week 9. So today you're going to look at the gas phase pressurized CSTR. This is application for chemical engineering. So you have to understand what's going on in here, and as usual we develop the equations that related to that process. And the second part of the lecture would be to solve the equation for non-isothermal CSTR, considering if it is like perfectly mixed cooling jacket, or if it's a plug flow cooling jacket. It's only the two parts that we can do this week, and then next week, which I'm going to put it in the island, would be the third and the fourth part of the non-isothermal CSTR. If we can finish it by today, we'll try to finish it by today, because I don't see that as a complicated method to develop the equation. Okay, now section 3.5 of your textbook. Okay, suppose a mixture of gas is fed into reactor, sketch in figure 3.2. so from your textbook, this is figure 3.2. The reactor is filled with reacting gas which are perfectly mixed. A reversible reaction occurs. So we are going to assume that this is the equation. 2A going to be, this is a reversible reaction. The forward reaction is 1/5 order in A. So this one is 1.5, 1/5, and reverse of that is the first order reaction, the first order of B. You can see that, yeah. Note that the stoichiometric coefficient for A and the order of reaction are not the same. Okay. Remember from the previous class, I think 2-3 weeks ago, the stoichiometry is not the same as the order of reaction. Okay. The mole fraction of reactant A in the reactor is Y. So this is the mole fraction of A. So this is the storage tank. Okay, this part is the storage tank. So this is actually the CSTR, gas phase pressurized CSTR. So Y is the fraction, Y is the fraction, the mole fraction of reactant A. Okay, the pressure inside the vessel is P, the pressure in the reactor is P. Both P and Y can vary with time, because this is a gas phase. Once your pressure change, then Y change. Okay, the volume in the reactor V is constant, so the volume is rigid. This is a rigid volume because the tank cannot expand or shrink. We will assume an isothermal system, so the temperature T is constant. Perfect gases are also assumed. So if this is not a perfect gas, then you have to use the equation of state, the one that you have learned in high Cs. Yeah? The feed stream has a density rho naught, okay, and a mole fraction Y naught of reactant A. The volume flow rate is F naught. The flow out of reactor passes through a restriction control valve into another vessel. So this is actually your valve, which is held at a constant pressure PD. So in here your pressure would be PD. The outflow will vary with pressure and the composition of the reactor. Okay, equation 3.14, that is actually the equation for flow. Okay, so the valve is actually controlled by this equation. Okay, or the flow is controlled by this equation using the valve. Okay, because your CV here is a valve sizing coefficient. Okay. Okay, sorry, it's here. Okay, now this is your CV. CV is actually your valve sizing coefficient, and PD is actually the pressure in the tank there. Okay, so oh no, this is not right. This is not right. The PD is in here. So the flow here will be depending on the equation just now. Now, density varies with pressure. Now, your pressure, your density here, this is a gas, okay? The density will always vary because you know we use the equation of state. So, if your pressure change, your temperature change, then your density easily can change. You can assume density is constant if you are working with liquid system, but never do that for gas system. So your density for the gas system will always change by using the PV is equal to nRT. Whatever lah, which one varies, because PV is equal to nRT, you have volume, you have pressure, you have temperature. And if this is not following the equation of not following the PV is equal to nRT, then you should actually consider the equation of state. Okay, the So Bradley and Kwong, the Peng Robinson, and things like that. Okay, now the calculation of density is given by this. This is actually the fraction, your reactant fraction. Okay, the Y is the mole fraction of your reactant, and to calculate density is MP over RT, and this one will change depending on your Y fraction. Okay, so as it reacts, A will be converted to B, and B can also be converted to A. So if A reacted, you will have less A and more B, depending on how you set the temperature of the temperature and the pressure of the process. Okay, so you want B is the product. Okay, so you have to have a specific temperature and pressure for more B to be produced. So the density will definitely change because it depends on how much A has been converted and so on. So density will change with time. Next, the concentration of reactant. Okay, now you can actually calculate the concentration of reactant of A by using Ca is equals to PYRT. So if your Y changes, the mole fraction of your product changes. Sorry, the mole fraction of your reactant changes to product, your concentration of A will change definitely. So in order for you to actually monitor your Ca, you will monitor your Ca and your Cb with time, isn't it? So this is how you calculate it. You have at P, you have your T, then you calculate your Y, then you got your Ca. This one is in mole per meter cube. It makes more sense. Okay, per meter cube. And units of moles of A per unit volume. Okay. Fraction is this one, RF forward. Remember, A going to B. Okay, so this is a K1, Ca to the power of 1.5, because here is 1.5, this is 1, right? So is equals to minus 1 over 2V. So we have gone through this one, yeah. So minus 1 over 2V. Hang on, the equation is, this is 2A. So this is actually the stoichiometric ratio, okay, for forward reaction for A, because we are actually measuring the concentration for A. Okay, and we have minus here because this is the reactant, equals to, this is the expression for product. So overall reaction rate is this. So if you want to do the balance, the component quantity equation, if you want to do the CCE for A, you take only this part. Is it? No, we are going to do this later after this, next page. So the total continuity equation is given by, write your general equation. So I'll give you 1 mark for that. The next one is d rho v on dt is equals to f naught rho naught minus f rho. Okay, because we are only measuring only one, we are actually measuring the TCE in the reactor only, in the vessel only. So the TCE is just like macam biasa we have done it before by using this equation. Okay, Then let's look at the component quantity equation. So we have again 2A going to B. So this is your K1, this is your K2. Now we have dVCA on dt. Oh yeah, because the volume is constant, we can confidently just put it up, just put it here, take it outside from the d rho over dt. The density will change, remember? Okay, now fine. Okay, now dVCA on dt is equals to F naught CA naught minus FCA. Now let's deal with the forward reaction, and then this is actually the backward reaction. Okay, the forward reaction is, because it's forward reaction, then we have the minus. We are doing it for A. Okay, then minus the 2 is from this stoichiometric ratio, the 2V K1 CA 1.5, right? Because we are doing balance for A. Then plus, okay, why we still have 2 here? It's 2V K2 CB. So this is fine, but why are we still have this one here? Let's go back to the overall reaction rate. So better you check your equation each time if there's a change in your stoichiometric values. So let's go back to this equation. Now if you want to do your, hang on, we're talking about A. When we want to do your A, one dNA over dt, please have a concentration at this equation. dNA over dt is equals to minus 2V, we put this one up there, 2V K1 CA 1.5. Now we want to do for dNB as well. Okay, now what we do is that this one, okay, for reverse reaction, because we are going to do for reverse reaction and we are going to do for dNA on dt. Okay, so it becomes dNA over dt is equals to 2V, you put it here, K2 CB. That's how it comes. Okay, so if you, this is for dNA for forward reaction, okay, for concentration, for A for forward reaction, and this is for A for reverse reaction. So if you want to do for B, then you take this one and that one. Okay, so that's why you have your dNA over dt is equals to plus 2V, put it in here. So that's why in here you have your 2 expression here. You understand? Tak faham? I repeat. Let me erase this one. So in here, this is the component quantity equation for A. So we know it's V dCA over dt is equals to F naught CA naught minus FCA. Now we are going to make to plug in the values for the rate of formation. Now that's where we have to go back. Okay, this one actually plus dNA on dt forward reaction plus dNA on dt reverse reaction. Okay, so this one becomes F naught CA naught minus FCA. Now let's go back. So for forward reaction, the dNA, this one, dNA on dt R is equals to minus 2V K1 CA 1.5, and then your dNA dt for reverse for forward reaction, sorry, this is forward, kan? This is actually reverse, so this is actually forward. So dNA reverse equals to 2V K2 CB. So you plug in this value into the equation just now. Is it okay? Okay, now let's do this. So it becomes minus 2v K1 CA 1.5 plus 2v K2 CB. So if you want to solve this, if you want to solve the density for this, then you have to plug in the equation from this one, in which the variable is y. It changes, and this equation, this y, is also you can actually convert that to the concentration later. You get the value of y, and then after that you calculate the CA, and at the end you can actually do this. This is how this is tied to the second equation if you do not have enough equation. When you want to solve this, usually you will need two equations, isn't it? You need the TCE, you need the CCE. So how you do that? You do this. Okay. Now let's look at non-isothermal CSTR. Something is very wrong with the diagram, because we copy and paste from, I think, the way when they convert it to from Word to PDF ni dia lari sikit. So let's correct this. So we don't we have this, we don't have that. So this is the jacket reactor, the jacketed CSTR. So that's the arrow. This is going one direction, and you have your K. In the reactors studied so far, we have shown the effects of variable hold up, variable densities, and higher order kinetics on the total and component quantity equations. Energy equations were not needed because we assume isothermal operation. So we only need the dynamic of the temperature when you want to measure the dynamic part. If not, if it's a isothermal, then you don't have any problem, because you know the temperature in equals to the temperature out, which is actually equal to the temperature in the system. So let us now consider a system in which temperature can change with time. An irreversible exothermic reaction is carried out in the single perfectly mixed CSTR as shown in figure 3.3 of page 47. The reaction is nth order in reactant A. Okay, so it's nth order of reactant A, and it has the heat of reaction lambda. Negligible heat loss and constant densities are assumed. So it is safe to assume this constant density in here, because this is a liquid system. To remove the heat of reaction, a cooling jacket surrounds the reactor. So we have a cooling jacket surrounding it. Cooling water is added to the jacket at a volumetric flow rate Fj. So this is actually the flow rate to the cooling jacket. In this case is water. Okay, now, and the inlet temperature of Tj0. So this is the inlet temperature of water surrounding the jacket. The volume of water in the jacket Vj is constant. So that's Vj, the volume. The mass of the metal wall is assumed negligible, so the thermal inertia of the metal need not be considered. This is often a fairly good assumption, because heat capacity of steel is about 0.1 BTU, which in order of magnitude less than that of water. Okay. A perfectly mixed cooling jacket. So we are going to look into 4 assumptions in here. Okay, 4 types of non-isothermal CSTR. The first one, we are going to assume that we have a perfectly mixed cooling jacket, the easiest one. Then the next one, we are going to assume plug flow cooling jacket. Okay, the lump jacket model, and significant metal wall capacitance. So in this case, the way we assume the T, how T is distributed in the cooling jacket would be different by following these 4 assumptions. Okay, so when you have in exam, say for example in exam, you have to look for the clue, which one you have to assume. If it's not given, you can assume anything. It is an open-ended question. Put down your assumptions, then just write down your equation. Now, for perfectly mixed cooling jacket, we know that the heat transfer, the Q, is very easy to calculate by using this simple equation, because you are considering the overall heat transfer coefficient, okay, for the heat transfer. If you want to be complicated, then you can actually consider the H, the K, the heat of conduction, the heat of convection, and so on and so forth. Then we have our AH there. AH is a heat transfer area. Then we have the temperature, the change of temperature between the hot and the cold. So in this case, because this is exothermic reaction, you know that your temperature in the reactor is hotter than the temperature in the water. It's a cooling process, so it's T minus Tj. You'll be safe. Okay, you use this formula, the hot minus the cold, and then you use the nomenclature, the sign convention. Okay, if it's heat is given to the system, plus. If it's taken out from the system, minus. So in this case, this is isothermal process. Heat is taken out from the system. Correct? Heat out lah, minus lah. Yeah, because it's an isothermic reaction kan. Heat has to be taken out from the system. So, minus. Okay? Okay. Now, let's do your TCE in here. So, you have, this is the TCE in the reactor. We are not interested to calculate the TCE and CCE in the jacket. Why? It's only water, right? So, in order for you to solve this energy equation, so for cooling, for the coolant, or for the apa itu panggil, the steam, okay, the heating element, the only thing that you're interested with is the energy balance, because you need to know what is the flow rate of your coolant that you have to supply to that system. The volume is already fixed, but the only thing that can take out the heat is whether you are supplying the high flow or low flow of your coolant. In order for you to do that, you have to do the balance, the energy balance in the system first, because you need to know what's the temperature, how does it change with time. Then you can actually formulate what is the flow of your coolant to take it out. The next one is TCE. The only thing that we are interested in is the TCE in the reactor. So this is TCE in reactor. So as usual, d rho v on dt is equals to F naught minus F, as usual. Then the next one, this is actually going from A to B. Then you can do both CCEs if you want to plot the CCEs at the end of the day. Okay, the CCE of A and B. So let's do this dCA on dt first. That is F naught CA naught minus F CA. Now let's deal with this. So this is the nth order of reaction. This is your K1. So it's minus V K1 CAN. Correct? Right? Okay, good. Now let's do for DCB. Oh, hang on. There's a V missing there. So V dCB on dt. You can actually, in this case, we don't say that whether the volume is constant or not. So if the volume is not constant, then you have to treat it accordingly. Okay. So dCB on dt is equals to F naught CB naught minus FCB minus plus V K1 CAN. Right? I think I'm more comfortable if we change this to, let's change this to, we don't separate the V, because nothing is said about the volume, right? It's not constant, isn't it? It's dv CA on dt, dv CB on dt. Now the energy equations. So you have to actually understand how this is actually balanced from the beginning, right? Write down the general equation. Now I'll give you 1 mark for that. Rho U KE plus PE plus apa? Rho V KE plus PE plus, yep, correct, over dt is equals to F naught rho naught, yeah, KE naught plus PE naught plus U naught minus F rho KE plus PE plus U. Lagi, next one, plus minus Q. Then it's isothermic reaction minus lambda V K C A N. Then the work part plus minus F naught P naught, right? Plus FP. After that you treat all this. No. Kalau plus minus kan, this is not a bracket, kita dah buka. We have already opened up the bracket. Right? Don't get confused with that, or else you're not going to get it. Then we cross. Oh God. Cross. We assume the work shaft all 0 and so on. Then we know that we're going to get the final equation, rho V CP dt. No, hang on. Let's not separate the volume. The densities and the CPs can be considered as constant. Rho CP dVt on dt. Oh. Now, let's do, hang on. Let's do here. Just a small part here. Rho CP dVt on dt is equals to F naught rho naught CP naught T naught, correct? Minus F rho CP T plus minus, which is UA T minus TJ, right? Okay, minus lambda VKCAN. So from here to there, you must know how to do this. So this is the energy balance in the reactor. Okay, everything in here is in the reactor. Okay, next one. So what we want to do is to increase or decrease the flow of the water to take out the heat. Okay, so that's what we want to do. So now the jacket energy equation. Again, you start from the beginning. Okay, you must know how to start from beginning. But in the exam, if you already derived the equation for, say for example, for reactor just now, you don't have to derive from the beginning for the jacket, because you already know, you have already shown it. Because to do this, it will take like a long time, at least 15 minutes of your time to do the derivation. So you can jump straight to the jacket. Okay, the jacket energy equation. And the jacket energy equation, please look back at your equation, at your figure, and it's rho V. The volume is rigid, it's not going to change. Rho V CP, this is all J. Rho J VJ CPJ, it's D Tj on dt equals to F naught Fj naught. Fj naught lagi rho naught rho j naught Cpj naught Tj naught minus Fj rho j Cpj Tj. Now the heat is taken from the reactor, so it's plus. Okay, depending on the system that you do. It's rho, everything is rho. Rho, sorry, the echo of my rho is not so echo. Macam tu. Now the heat is taken up. Okay, you the coolant will receive heat from the reactor, so plus. Just now we said minus because you are doing balance for the system, the fluid. That's why you say that the heat is taken out. Heat is released because of the reaction. Okay, you have a lot of heat there, you want to release it, so you have to put in, you have to give it away, so it's minus. Now as a coolant, you want to cool off the system, so you are going to take the energy will be received by the coolant, so it's plus UA H. H is the heat transfer area covering the cooling the cooling water, the one that, the area that is in contact between the cooling water and the reactor. Still hot minus cold, in this case T minus Tj, then you'll be okay. Okay, you keep it to this. Okay, now the flow, the in and out of the flow from jacket is always constant. Okay, you can actually you can actually simplify this equation. Fj naught rho j naught Cpj naught Tj naught minus Tj plus UA H T minus Tj. Yep.
H is nomenclature or parameter?
Sorry, apa?
H tu nomenclature saja ke?
It's a common it's a constant heat transfer area.
Area for,
Yeah, if you have a reactor, then you have a cooling jacket like that. Your heat transfer area is like this area, the one that is in contact.
so that one is AH lah.
Yeah, sorry, it's AH, not A and H another thing. No, it's a nomenclature, the same nomenclature, because that's how they define it in the textbook. So that's why I just do it here so that you won't confuse. This is the heat transfer area. Okay, so what is your known parameter? Density you tahu, rho j naught you know, Cpj you tahu. Okay, and the Tj naught you know definitely because it's water. You do not know your Tj. Your U you know already, your AH you know already. So in this case, the one that you do not know is your Fj naught, which is also your Fj, and also your T, Tj on dt. So your Tj will be depending on how big the flow is. So in order for you to take out the Tj, now you have your T here. Your T here is also something that you do not know, because in order for you to find T, you have to go to the energy balance for the reactor. You have to solve that one first. So you have dt on dt, dt on dt, blah 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 blah. So some you have some is unknown, some is you do not know. So you have to solve your dt. In order for you to solve your dt, you have to solve your Ca. Remember? Because in your dCa, in dt, you have the value of Here, your K.
Oh.
What is the equation for K? So this is actually a function of K. This is the Arrhenius equation. So your K is actually lambda alpha exponential minus EA over RT. Remember, in order for you to find your CA, it is very much depending on your temperature there. You will actually run this within a range. So you have to solve for your CA. So you have to solve for your T. It ties. So once you solve for volume from your TCE, you can solve your CA. Then you can solve for your T, temperature of the reactor. Then after that, you can actually manipulate your TJ. So this is a complicated equation. Use your Excel. Use your iteration method. Very easy. Oh, in this case, you have to solve it by using Euler method. Euler or Runge-Kutta. Then you can see how the graph is. Then you can select, okay, I want this at this time T. So that is the parameter I want. So then you can actually decide this is the best flow and so on and so forth. Okay? Because everything you have to plot everything. You have to plot the graph on the. You have to plot all the parameters. Your the volume, how the volume changes. If it's not. The volume does not change, you are lucky. Then you have to put in the volume, the CA, the CB, the temperature of the reactor and the temperature of the jacket in one graph. Then you know how it change with time. Then you can decide. Okay, now from here, what you have to do, you draw a graph. Okay, now you have dV on dt. You have dCA on dt. You have dCB on dt. Right? You have dTJ on dt. And you have dt on dt. Everything, the denominator is time. This is time. So you do this. Okay, now you plot the graph. So you have volume CA and CB ni boleh sekali because the value will be almost the same. And then you have your TJ and your T. So macam ni lah. Like that. Like that. Like that. Satu naik atas. Satu like that. Like that. You decide lah. But your FJ not tu you have to guess first. You have another checking parameter. Do you know your tau? Your residence time? Okay, your tau V over F, right? So your tau is actually your T in here, because your tau here actually represent how long the fluid will be in the reactor. So once you have actually got your F, your V, F and so on, then you check by using this equation. So is it okay by that volume? You use that flow rate. Does the volume can cater that? Your tau ni is actually your T. So those are actually, I'm not going to show you how it's done one by one. It will take a long time for you to understand it. But I want you to have some idea how it is done. How it ties. Bukan you can imagine kan. So if you don't have enough equation, I'm sure you know how to find more equation. For example, heat transfer area AH. That is actually depending on the height and the diameter of your reactor. If your height changes, your AH change. If your volume change, the V change, then your AH will change, isn't it? So you put in that as the unknown. Okay? I want you to have some idea how it can be solved. We are not going to do that in this class because it will take a long time. Okay, the next one is if we are assuming that the jacket, the flow of the jacket, the flow of the coolant in the jacket is taking the plug flow system. So just now we are assuming the temperature at the whole of your jacket tu is constant. Maknanya temperature yang masuk in temperature at the FJ0 and temperature out is the same. Just now, because we only have one equation. We only have dTJ on dt only just now. Now in this case, you know for the fact that the temperature near the inlet is not the same as the temperature outlet. But now we are assuming that the temperature of the coolant in the whole system of the coolant yang in contact with the reactor, it has the same temperature. The TJ0 is something that you measure before dia masuk. We are talking about, kita kata dia uniformly ni, but in real life you know that's not true, definitely. So that is the simplest assumption that you can do just now. But now this one, we are trying to be smarter in this case. So what we do is that, say for example, you have a reactor and then you have a coolant, and in this case we are assuming that this is your TJ0, this is your TJ exit. So we are assuming that your TJ, the temperature in the coolant here is expressed by TJA, which is actually the average of in and out. You want to be smarter. So this one is a little bit better than the assumption before. You understand what I'm trying to say? Okay, now. So the TJA here is TJ0 plus TJ exit over 2. So in this case, if you want to do the balance for TJ, it's become dTJA on dt. Blah 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 blah. Just now it was dTJ on dt only. Kita assume whatever out is the same as whatever even in here. Even in here, your T is TJ already, which is not. It is way off lah. If you are talking about you are going to cool down about 60 ton of fluid, definitely it's going to be off. If you say you're going to do this model only for 100 milliliter reactor in the lab, this is applied. The first assumption tadi is okay, because it's a very small reactor. But in the plant, it's not possible, because your temperature will be off. Now, do I have to go through for this? No, don't need, isn't it? This is fine, right? You just have to replace your TJA, the temperature just now for coolant, with TJA on dt. Let's talk about this again. So if you want to assume this is taking the principle of plug flow cooling jacket. Plug flow means that it takes up the plug flow principle in the pipeline. So say for example, you have a large, if you have a pipeline, okay, taking the principle of plug flow, meaning that it's a reactor, plug flow reactor for example, it's just in a pipeline. So say for example, for reactor, then you have some the conversion going on from A to B. Definitely the temperature would be different. So the temperature in is not the same as temperature out. So how you do this, if you want to make things simpler, how you do it is that if you want to do the balance for temperature in the plug flow, you do dt on dt is equals to, no, hang on, this is T average, okay? Your T average is actually T in plus T out over 2. That's how you do it. So by taking the same principle, okay, assuming that the coolant, okay, going in from here to there by using a plug flow principle, we are taking the same assumption as well. Meaning to say that if you want to do the balance anywhere in the coolant, you will say that this is TJA, this is the average, the temperature of the jacket is average, is equals to TJ0 plus TJ over 2. So when you want to do the balance, when you want to develop the equation, it's going to be rho Cp, rho J, okay, CPA, okay, V is V lah, volume is constant, dTJA on dt is equals to F J0 rho J0 CPJ0 TJ0 minus FJA rho JA CPJA TJA. Then we the heat is received plus U AH T minus TJA. Okay. And you know your TJA at the end of the day. You solve for this one first, then you know your TJA is actually the average of out and TJ exit over 2. So that is the second assumption. The first assumption just now, we are saying that we are assuming the temperature of the jacket from start, once it's in there, and the exit is the same, TJ. Now we want to be smarter than before. We divide into 2. We have moved closer to the accuracy of your actual temperature. Okay, we have done this. So you know, this is just now, it should be dTJA on dt. So this one, the process fluid, is dt on dt. Okay, hang on, this is energy balance. So this one is here, ni title here. So this is dCA on dt, dCB on dt, this is dV on dt. Next one. Okay, this is just like what we said just now lah. The known parameter, the forcing function, and so on and so forth. Okay, you can get it from your textbook. That is required when you want to solve this equation. Which one is known? Macam your volume of your jacket is constant, that is a known parameter. Okay, and your CP, your rho, it won't change. So forcing function is something like F naught, Fj naught. This is something that you can change. Okay, it's a variable, but you yang buat the changes. So unknown, it's F, it's T. This one, Tj naught. It's all forcing function. You do the changes. Something that you have to guess. You try this one, dapat apa? Macam tu, lebih kurang. Okay, now the unknown is F, the T, the Ca, blah blah blah. Okay. Alright. Now the next one is lump jacket model. Lump jacket model means that you are going to divide your cooling jacket into different section. So you can, if you want to be, this is something very close to microscopic balance, but we don't use Del. This is still bulk. Maknanya if you have like a tank like that or a reactor like that, you divide into section, you section it according to the height, but still you do it in bulk. Say for example, this one, in this example, they divide into 4. You can divide into 10 or 20, or depending on how large your reactor is. So say for example, this is every 1 meter. Say for example, this is a 4 meter reactor. So 1 meter, 1 meter, 1 meter. This is still a macroscopic balance. Macroscopic balance. If we are talking about microscopic balance, you have to divide it to a smaller number. Say for example 1 cm. So the change is quite accurate with height. Now when we have this, meaning to say that, okay, we can write the energy balance like this. So this is the first section, this is the second section, this is the third section, this is the fourth section. Now let's go back to that. So this is your Fj naught, this is your Fj naught, this is your Fj, this is your Tj. But in this case, because you have actually divide this into section, the last Tj is Tj4. So this one becomes Tj4. We are assuming whatever inside is equals to going out of the system. Now this one becomes Tj4. This is Fj naught. Okay, now the inlet is Tj naught. The outlet from this system is Tj1. This one, remember, the outlet is the same as whatever in the system. So the outlet is Tj1. So for this case, it's become Tj1 minus Tj2. The outlet from the second lump, we call it as a lump because we lumped the jacket according to cross-sectional area. You can view this, right? So going out of in here for TJ3, going out coming into TJ3 is TJ2. Out from TJ3 it's TJ3 lah, because it's uniform, and so on and so forth. So in order for you to do this, your Q is the same. Okay, your Q is the same. You can actually your total Q is actually the summation of Q1 to Q4. You bahagilah, bagi 4. Okay, you bahagi 4. You can use Q1, Q2, Q4 ataupun 1/4 of Q. Does not really matter. Depend on how much is your lump. So in this case, let's look into the equation. Okay, we have 1/4 in here, which represent a quarter of VJ. Initially we have only VJ, right? VJ is representing the whole thing, so we divide into 4 because we are taking the 4 lumps in this case. 4 lumps model, ada 4. If you want to do 10, you divide 1/10. And you have the TJ1 coming into the first section, the first lump. And then this is K. If J0 rho J CJ is the same, we are assuming that F J0 is equals to Fj, rho J0 is equals to rho J, and CP J0 is equals to CPJ. So this one becomes TJ0 minus TJ1. Okay, this is the assumption. Sama it's the same because we are saying that this is the perfectly mixed system. Okay, plus the heat is accepted from the heat is received from your reactor, and we divide into 1/4 because the heat transfer area is divided by 4, and this is actually the expression for your Q, your Q1, right? Your U remains because dia tak ada kena mengena dengan you punya the division of it. And this one becomes T, the temperature in the reactor, minus TJ1. So once you have this, you will see how does the temperature change from TJ0 to TJ1 to TJ2 to TJ3 to TJ4. Then you know how does it change, the profile changes. This is more accurate. This is the accurate lah, the most accurate compared to the other two that we assumed just now. Okay, so please have a look at page 50 of your textbook. So the last section, the significant metal wall capacitance. So what really happened here is that we are going to assume that this is the wall, okay, of surrounding the fluid. Okay, so this is the process fluid section. So this is the wall, and this is the jacket. So in this case, from last week's class, so we are saying that this is a non-isothermal CSTR, meaning to say that there's a reaction occur in the process fluid, and we have looked into 4 types of modeling that you can actually adopt it. And the last one is when we assuming everything is a lump. Okay, so in that case we are considering the effect of the metal wall through the modeling. Okay, for the last 3 sections that we have done, we do not actually consider anything on the effect of the metals. So in this case, we are going to look into Q, the heat dissipated from the reaction, okay, from the fluid is transferred to the metal wall. Then from the metal wall, it transferred to the jacket. So in this case, you are supposed to model 3 types of equation. The first one for energy balance, okay, the first one you have to do the energy balance for the process fluid, then you do the energy balance for the metal, and the next one energy balance for the jacket. So So the temperature of the process fluid is T, the temperature of the metal wall is Tm, and the temperature of the jacket is Tj. So for example, if you want to lump this into 4 sections or 10 sections, you can also do this. It's the same thing, meaning to say that if you're referring to the last week lectures, meaning to say that you're going to divide that into sections, because you know the temperature here, this section is definitely different with the temperature in here. Okay, all right. Next, so from here, this is supposed to be very easy. So there are 3 energy equation for the process. This is for process, d rho v dt over dt, okay, is equals to rho Cp F naught T naught minus Ft. You're okay with this? Yes. Minus, this is actually the heat dissipated by the reaction. This is exothermic process, so that's why you have a minus section there, right? Minus lambda V Ca, okay, and this is the expression for K. Initially it's minus lambda V K Ca to the power of n. Minus, okay, now please note the sign. The heat is dissipated means that the heat is given away from the process fluid. So giveaway is minus. So that's why you have the minus sign kat situ. Then the hot fluid minus the cold side of the system. That's why you have a T minus Tm. Are we okay? Yeah, all right. So let's look at the metal, the energy balance for the metal wall. Now it's rho m v m cm. So this one is the heat capacity for metal, the volume of the metal, and this is the density of the metal, equals to times dTm on dt. Okay, remember the temperature of the metal also change with time. So if the temperature of your fluid changes, then the temperature of metal wall will change with time as well, which is actually will be transferred to your jacket. And equals to, okay, in this case you only have heat in and heat out for metal wall. You don't have anything flowing to the metal. Okay, it's only heat in and heat out. So in this case, the Hi is the heat transfer film coefficient times with the heat transfer area from the inside of the metal times the temperature of the hot minus cold. Okay, and this one, the incoming for the metal, the incoming heat for the metal is received, right? You have a fluid there. This is your metal, this is your jacket. So in this side, heat is received. So this is your Tm. Okay, and in here, heat is dissipated. So when this is received, this is plus. When this is dissipated, this is minus. That's why you have plus here and you have minus there. Okay, you don't have to remember this. You don't have to remember the equation. Just understand the concept. That's all you have to do. Okay. Now, this one always hot minus cold. So the fluid is hotter than the metal wall. And minus the H naught. This side you have H naught, this side you have H1. H naught times A1, times A naught. This is A naught, this is A1. A inside, AI times the hot. The metal is hotter than the jacket, so Tm minus Okay, the next one, we look at the equation for the jacket. So in this case, I think it's water. From last week, it was water. So it's there's something flowing in. Okay, so this one is the expression for the unsteady state expression. You have rho j, vj, cj, dtj on dt. Okay, and equals to, this is the flow of the jacket coming in. Okay, the flow coming into the jacket is assumed to be the same as the flow going out from the jacket. There's no volume build up in the jacket. Okay, in this case we are assuming that Fj0 is equals to Fj. So that's why we lump everything together here. So it's become Fj rho j Cj times Tj0 minus Tj. There's no reaction in the coolant. No reaction for coolant. No heat no heat generated by the coolant. Heat is only received and taken out from the coolant. Okay, so in this case, the heat is received by the coolant. So that's why you have plus there. And again, H0, A0. Okay, and you have Tm minus Tj. The hot minus the cold. This one represent out, not initial. The A out here, the A out and your H out between the wall and the jacket. Jacket is the coolant. It taken out heat.
Dia sendiri tak generate heat lah.
No, because heat is only generated when there's a reaction. Remember, you have exothermic process, endothermic process. Heat are generated by the chemical reaction. A reacts with B producing C. In order for them to react, heat must be released. So the heat released tu yang we have to capture. We take it out by supplying the coolant next to the fluid. It's just like you have a hot tea, you want to drink it but you don't want to add ice in it, so you put that inside a bucket with ice. So heat is taken out by heat of your ice, of your tea, okay, was taken out by the ice, the bucket of the ice, but you don't want to put the ice inside. It's just like that. So in this case, the heat is generated because of the reaction. When you do your high Cs, remember, when you don't have your Q, you letak the reaction, and suddenly I ask you, endothermic or exothermic, because suddenly the outside temperature suddenly is going up or going down. So when the outside temperature from the reactor without the Q going in or out, okay, no, Q represent the coolant, okay, the coolant or the steam, whatever we supply. So without that Q value yang you masukkan dekat dalam you punya reactor, your temperature outside changes, tinggi. Means that is the temperature without the effect of coolant. And you have to bring down that temperature, because if the temperature high, then your yield would be down, because everything is depending on this value. K tu dia ada dia punya limitation. The K, the specific reaction rate, it has its limitation for the reaction to proceed or not to proceed, depending on the temperature range. So that's why you have to always control the temperature of your reactor. You don't want it to exceed or below the temperature you want, or else nothing happen. Reactant in, reactant out. Next. Oh, we are done. That's it.